This section, we're going to go over some measure of position and how they're used. And before we begin, I'd like to ask a simple, straightforward question. Who is taller? A man who's 73 inches tall, or a woman that is 68 inches tall? And this is not a trick question. You can kind of see that 73 inches is bigger than 68, but typically men are taller than women. So this is not a fair comparison. So we have to ask ourselves a new question. Who is taller relative to their gender? And this is a more interesting question because we can't just look who has the most inches. We have to consider that men, on average, are taller than women. So how do we answer this question? We have to come up with a new method. And something that we're going to talk about is z-scores. So one way to answer this question is z-scores. And that's what we're going to talk about next. So what is a z-score? Well, a z-score kind of tells you the number of standard deviation that data value is from the mean. So how do you find your z-score? Well, with a z-score, for a specific data value x, we have to use this formula. So it's x, which is your data value that you want to compare, minus the mean of your population over the standard deviation of your population. So there's some properties for z-scores. So if your z-score is really close to 0, that kind of tells you that your data value is near the mean of the distribution. And if you have a positive z-score, then you're above the mean. And if you have a negative z-score, then you're below the mean. Another way that you want to think about this is that, let's say there's a number line. Let's say right here, this is your mean. So if your z-score is on the positive side, so that means that your z-score is above your mean. But if your z-score is on the negative side, visually, so let's say this is your mean, your z-score is lower or below the mean. So let's go over an example. So there was this study that stated that the mean height for adult men in the United States was 69.4 inches with a standard deviation of 3.1. And the mean height for adult women in the United States is 63.8 inches with a standard deviation of 2.8. And we want to ask ourselves, who is taller relative to their gender? A man who's 73 inches tall or a woman that's 68 inches tall? So the first thing we have to do is collect our information. So we know that the mean height for men in the United States is 69.4 inches because that's what we got from the question. And the standard deviation for men's height in the United States 3.1 inches. We can also know that the mean height for women is 63.8 inches with a standard deviation of 2.8 inches. And again, that's the information that we collected from the question. So now we want to do is calculate our z-score. The z-score for the man's height, if you look at the formula, it's the data value minus the population mean over the standard deviation. So this will be 73 minus 69.4 over 3.1, which gives us 1.16. And remember, I got this 73 from the data value that we're comparing it to, which is the man who's 73 inches tall. And so we want to do the same thing for the woman's height. So the z-score would be their data value minus the population mean over the standard deviation, which is 68 minus 63.8 over 2.8, which gives us 1.5. And remember, I got this 68 from the data value that we're comparing it to. These z-scores tell us how many standard deviation away are you from the mean. And it's clear that the height of the woman has a larger z-score. So in words, we could write that the height of the 73-inch man is 1.16 standard deviation above the mean, while the height of the 68-inch woman is 1.5 standard deviation above the mean. If you look back at the definition, since our z-scores are positive, we know that they're above the mean. And so the z-score for women is a lot higher than the z-score for the man. So we know that she's more above average. So to answer the question, we see that the woman is taller than the man relative to her gender. Also, the idea of z-score kind of goes back into empirical rule. So if your population had a histogram that was symmetric, or another word for symmetric is normal, then a couple things applies. Then we know that 68% of our data will have a z-score between -1 and 1. We know that 95% of our data will have a z-score between -2 and 2. And 99.7, or almost all of our data values, will have a z-score between -3 and 3. Next, I want to talk about quartiles. And what quartile does is that it actually divides your data set into 4 approximately equal pieces. So there are 3 quartiles. The first quartile, we call it Q1. So this separates the lower 25% of your data from the high 75%. And also the second quartile, we call it Q2. So this divides half of your data set. So that's why we call it the median. So the quartile 2 is just computed the median, which we've done in the previous sections. And their quartile separates the lower 75% of our data set from the highest 25. So how do we compute this? Well, there's actually multiple ways, or there are actually several methods for computing quartiles. And then for this section, I'm going to show 2 ways. Let's consider this example. We want to find all of our quartiles, so quartile 1, 2, and 3. First thing we want to do is arrange our dataset from least to greatest, but since they already done that for us, that job is done. Next, we want to consider finding the median of our dataset, because the median is also our second quartile. In this case, Q2 is 7. Next, we want to find the median of our lower half of our dataset, because that will be our first quartile, or quartile 1. And then here, the median will be a number between 3 and 4, so we take the average, which is 3.5. So our first quartile is 3.5. Next, we want to find quartile 3, which is the median of our upper data set. In this case, it's the average of these two numbers, so it's 8.5. So quartile 3 is 8.5. So now we find all of our quartiles. One thing you want to notice is that this method only works for smaller data set. It doesn't really work well for larger data set. For bigger data sets, you want to consider a different procedure. So here's a little instruction of how to compute your quartile when you have larger data set. So the first thing you want to do is arrange your data set from least to greatest. Then you want to know how many values there are in your data set, or how many observations there are in your data set. We're going to call this n. To find the first quartile, you want to compute this number here, which is 0.25 times the number of values in your data set, or n. And if this number, L, if it's a whole number, then your quartile is the average of the number in position L and the number in position L plus 1. Think of L like the location of your quartile. This is location of your quartile. If your L is not a whole number, say it's a decimal, then you want to round up to the next highest whole number. And that number will be the location of your quartile. Notice that you always round up. It doesn't matter if, for example, if you compute your L and you get something like 8.2, you still round it up to the next highest whole number, which is 9. And this number just represents the location of your quartile. And you do the same thing for the second quartile and third quartile. But for the second quartile, you want to multiply it by 0.5 times the number of observation. And for the third quartile, you want to compute 0.75 times your number of observation in your data set. And the reason why we're doing this is because these number represents the lower 25% of your data set, the middle of your data set, and the upper 75% of your data set. Let's consider this example. So notice this table is the annual rainfall in LA from 1969 to 2013. And notice that in our data set, it's already arranged from least to greatest, so that part is done. We want to compute first, second, and third quartile. Since our data set is really big, we kind of want to use the procedure that we talked about earlier. And the first thing we want to do is count how many observation or how many data values there are in your data set. This value is your N, which is 45. Next, you want to compute the first quartile, or your Q1. To do that, you want to compute this L, which is 0.25 times your N. And if you do the math, this gives you 11.25. Since this is a decimal, we have to round up to the nearest whole number, which is 12. So quick question here. Is this value our first quartile or our Q1? And the answer is no. Remember, this is the location of where our first quartile is. It's a very common mistake that student thinks that this value is our quartile, but it's not. It's the position or the location of where it is. Think about it as L is the 12th position or location in our data set. So if you look at our data set and you look at the 12th number, which is 0.92, this here is your first quartile. So Q1 is 0.92. Next, you want to compute your second quartile, or your Q2. And similarly, you want to compute this L, which is 0.5 times your N, which gives you 22.5. Since this is a decimal, you want to round up to the nearest whole number, which is 23. We always round up. So, same question. Is this value our second quartile or our Q2? And again, the answer is no. This number represents the location or the position of our second quartile. Again, this is a very common mistake, so just be aware of it. So you can say that L is your 23rd position or location in your data set. So you go up to your data set and count the 23rd number. In this case, is 3.12. So 3.12 is your second quartile. Finally, we want to compute the third quartile, or our Q3. So again, we want to compute this L, which is 0.75 times your N, which gives you 33.75. But again, we want to round up to our nearest whole number. Similarly, this is not our third quartile value. This is the position or location of where our third quartile is. So again, you could think about it, this is the 34th position or location in our data set. So you want to go back into our data set and count the 34th number. In this case, is 4.94. And then after that, congratulations, we just compute all of the quartiles. So something that's related to quartile is something called percentile. So remember that quartiles divide your data set into four equal parts. Percentiles divide your data set into hundreds of equal parts. So for a number p between 1 and 99, the pth percentile separates the lowest p percent of the data from the highest 100 minus p percent. So when people talk about SAT scores, if you're within the 30 percentile, so that means you beat 30% of the competition, or you've done better than 30% of the people who took the SATs. So that's what people talk about. So how do you compute percentile? Well, it's very similar to how we compute quartiles for a larger data set. So you have to arrange your data set from increasing order, or from least to greatest. And then we want this n to be the number of observation in your data set, or the number of values in your data set. So for the pth percentile, we want to compute this L again. So this L will be p over 100 times n, where p is the percentile that you want. If this value L is a whole number, you want to take the average from the Lth position and the L plus 1 position. If L is not a whole number, again, you want to round up to the next whole number, highest whole number, and that will be the location of where your desired percentile would be. So for example, again, if your L was 8.2, you always round up to the next highest whole number, which is 9. Let's say you want to know the 60th percentile from the LA rainfall data set that we worked on earlier. So we have to compute our L, which is 60 over 100 times n, and this will be 27. And notice that this is a whole number. So we have to take the average between the L and L plus 1 position. So here, since this is a whole number, so the 60th percentile is the average in the 27th and 28th position. We're just adding 1 from 27. If you look back into our data set, the 27th number will be 3.57, and the 28th number is 3.71, and so the average is 3.67. So this is our 60th percentile. One thing I want to talk about is the 5-number summary. So this is a very simple concept. It's pretty much just the 5 summaries of our data set that consists of the minimum number, the first quartile, the median or the second quartile, the third quartile, and the maximum. Since the second quartile and the median are the same, we could just write either or. So once we compute this, we want to order them from the smallest value to the largest value. So let's look at this example here. Let's say you have these exam scores from 11 students from a stats class, and you want to construct a 5-number summary. Notice that they're not in order, so that's the first thing you have to do is put them from least to greatest. And once you do that, we want to find the median or the second quartile, since that should be easy. And so our second quartile is 85. Since this data set is pretty small, we're going to use method 1 to find the first and third quartile. In this case, the first quartile is 64, since it's the median of the lower half. And so the third quartile is 92, since it's the median of the upper half. And since 47 is the minimum and 99 is our maximum, we have computed the 5-number summary of our data set, and they're already from least to greatest. One thing I want to discuss is something called outliers. And what most people think outliers are values in your data set that is extremely large than any of the other values in your data set. And that's actually a common misconception. It goes both ways. An outlier is any value that is extremely large or small than any of your values in your data set. But how do we check for outliers? How do you know that your values is quote unquote large enough or small enough to be an outlier? Well, there's a method for that. And we need something called an interquartile range, or IQR for short. And this is another measure of spread. And to compute your IQR, you need to find the difference between your first and third quartile. So here, your IQR is just your quartile 3 minus your quartile 1. And then once you computed this, you want to compute something called an outlier boundaries. So these boundaries are your cutoff points to determine whether or not they're outliers. So what you do is compute your lower boundary. So this is done by getting your quartile 1 minus 1.5 times your IQR. So what this tells you is that any value that is less than this number or less than your lower boundary is an outlier. And also, you need to compute an upper boundary, which is just your quartile 3 plus 1.5 times your IQR. So this number tells you that any value in your data set that is larger than this number or larger than your upper boundary are considered outliers. So that's a way to identify outliers. So let's see from the LA rainfall data set that I've been working on and see if there's any outliers from that data set. We already been working with this data set, so we already know what our quartiles are from the previous examples. So here, we know that our quartile 1 and quartile 3 from the previous example. So our quartile 1 was 0.92, and our quartile 3, well, that should be a 3, is 4.94. And now we could compute our IQR, which is this difference between quartile 3 and quartile 1. And if you do the math here, if you subtract these numbers, this should be 4.02. So this is your IQR. And we need this value to compute our boundaries. So let's compute our lower bound. I'm just going to call it LB, which is quartile 1 minus 1.5 times our IQR. But we already know our IQR, so we just plug that number in. So once we computed this value, this will be negative 5.11. And then again, we want to do the same thing for our upper bound, which is our quartile 3 plus 1.5 times our IQR. And again, we already know what our IQR is, so we plug in that number. So this value should be 10.97. Then you want to ask yourself, are there any values in our dataset that is lower than negative 5.11 or higher than 10.97? And there actually are. There are 3 numbers that are higher than 10.97. So these values are your outliers. So we talked about quartiles, IQR, outliers. So what we could do is put them all together with something called a box and whisker plot. So what is a box and whisker plot? It's actually a graphical display of our 5-number summary. So constructing a box and whisker plot, we want to draw a box from our first quartile and our third quartile. And then we want to draw a solid line in the box that represents our median. And then we want to compute our lower and upper boundaries because we want to identify any outliers in our data set. So once we do that, we want to draw a line, also called a whisker, from our first quartile to the smallest data value that is greater than the lower boundary. And very similarly, we want to draw a horizontal line from our third quartile all the way to the largest data value that is less than our upper boundary. And then finally, we want to identify any outliers by putting like a little dot or a star, just something to tell me like those values are my outliers. So let's do an example. To make a box and whisker plot, we need to figure out a couple things first. We need to find the 5-number summary, the IQR, to identify any outliers. I would recommend pause the video and do this on your own since we already done a lot of examples of these. To find the 5-number summary, first thing we have to do is arrange our dataset from smallest to largest. Luckily, I already done that here. To find our quartile, let's use method 2 for this. So we're going to use method 2 to find our quartiles. We have to know how many observations there are in our dataset, and here is 22 observations. We want to find our first quartile, so we have to compute our L, which is 5.5. Since this is a decimal, you want to round up to the nearest whole number. So this means the 6th number in our dataset is our first quartile, which is 45. So our first quartile is 45. Then we want to find the second quartile, and so we have to compute our L, which is 0.5 times 22, which is 11. Notice that 11 is a whole number, so that means we have to take the average between the L and the L plus 1 position. In other words, we want to take the average of the 11th position of our data set and the 12th position of our data set. So here, the 11th number is 51 and the 12th number is also 51. So you take the average of these two numbers. So our second quartile will be 51. To find the third quartile, we need to compute our L, and this will give us 16.5, which we round up to 17. So the 17th number is our third quartile. So in this case, it's 59. Then you want to find the minimum and maximum value of your data set. So here, the minimum value is 41 and the maximum value is 100. And so you just finished computing the 5-number summary. So let's put them in order. You have the minimum, which is 41, your first quartile, which is 45, second quartile, 51, third quartile, 59, and your maximum, which is 100. To find your IQR, you need to subtract your third quartile from your first quartile. So subtracting 59 minus 45 gives you 14. So your IQR is 14. You need this number to identify any outliers because you need to compute your lower bound, which is your first quartile minus 1.5 times your IQR. And so if you plug in your numbers, this should give you 24. And again, you want to do is compute your upper bound, and if you plug in those numbers, it gives you 80. You want to look at your data set and see if there's any number that's higher than 80 or lower than 24. In this case, 100 is much higher than 80. So yes, 100 is an outlier. Now that we have all the information that we need, it's time to construct a box and whisker plot. So the first thing you want to do is number your number line. So this should be 40, 50, 60, 70, 80, 90, 100. And notice that they're all equally spaced. Next, we want to actually label our axis. So this should be number of absent students. Okay, so now it's actually time to draw our box and whisker plot. So we want to draw a box between our first quartile and our third quartile. So the first quartile was 45. So I'm going to put a line here at 45. and our third quartile was 59. So I'm gonna draw a line here at 59, and I just want to connect them to make a box. So this is our first quartile, and this is our third quartile. Because quartile 1 was 45, so somewhere around here, and quartile 3 was 59, so somewhere around here. Next, we want to draw our second quartile, or our median, with a straight line. And remember, our second quartile was 51, so it should be around here. So once you have this, we want to draw our whiskers. So let's look at the left whiskers. So we want to draw a line all the way to the smallest value that is a little bit bigger than our lower bound. So in this case, it's 41, somewhere around here. And then to draw our right whiskers, we want to draw a line to the largest value in our dataset that is actually less than our upper bound. So in this case, it's 77. Notice that I didn't go all the way to the maximum value in my dataset, which is 100. I'm actually going to the maximum value that is less than our upper bound. So our upper bound was 80, so the maximum number a little bit less than that was 77. And then again, this was 41. The last step is that you want to identify any outliers. So if you remember, 100 was an outlier in our dataset, so we want to identify that by a little dot or a star. And congratulations, we just made a box and whiskers plot.